Hi class, let's work on some prepare questions. The first one here I have is cis-1,2 cyclohexane diol from cyclohexane. So first things first, you obviously should draw it out so you know what you have and where you want to go. Since it's a cyclohexane diol and it's cis, that means there are two OHs both pointing in the same direction. And cyclohexane, of course, is a six-membered ring. Realize when you're thinking about cyclohexane, it's very similar to a regular alkane. That means there's no functionality. If you mix this with water, it's just going to look at it, do nothing. No reaction is going to take place. So this is a pretty saturated type of a compound, not willing to react. You can make it to react by introducing polarity in this molecule. One way to do that is to treat this with bromine and light, and the reason you would want something as rigorous as bromine and light, something very free radical like, so if you just take HBr, that's not going to cut it. The reason why you would want to use very rigorous conditions is again because it's an alkane, cycloalkane. They do not want to react just like that, so you have to make it go. Now once you have established that bromine on the cyclohexane, when you treat it with a base, so recall your Baha, bases on alkyl halides, and acids on alcohols, both of those give you the double bond. And that's going to give you your cyclohexene. It should have occurred to you anyway when you looked at the target molecule. The target molecule is a cis diol, and the only way we have talked about to get that is through cyclohexene. If you subject that to treatment with osmium tetroxide, pyridine, and you follow it with sodium bisulfite and water. So you know that if you have cyclohexene, this reaction condition, this very specific reaction condition, is going to give you your cyclohexane diol. So now that you have the double bond, just subject that to that reaction condition and get your target molecule, and that is it. Now if you were asked to get, instead of the cis diol, if you have a trans diol, of course then you will have to go the epoxide route. So you could treat this with MCPBA, follow it with hydrolysis. When you do just the MCPBA, it's going to give you the epoxide, and then that epoxide upon treatment with hydronium ion is going to give you a trans and a cis OH. I'm sorry, I meant to say an OH up and down. Okay, let's try another one. 2-methylpropene from acetone. So acetone, we know, is a 3-carbon chain, has a C double bond O, so it's 2-propanone. 2-methylpropene would be, that's propene, second position has a methyl. So if you count the number of carbons, you have 4 carbons in your product. You have only 3 carbons in your reactant. So obviously you have to add carbons. And you know that one way to add carbons is through Grignard reagents. And that would mean that you would have to treat it with CH3-MgBr, since it's only 1 carbon away. Hydrolyze it. And a ketone is supposed to give you a tertiary alcohol, and now just carry out a dehydration. So concentrated H2SO4 or POCl3 or H3PO4, whichever is going to give you your desired product. 2-cyclohexyl 2-butanol from acetylene. Acetylene is HC triple bond CH, so ethyne is also called as acetylene. That's a common name. And we have 2-cyclohexyl 2-butanol. So let's draw that out. Second position has the cyclohexyl, second position has the OH, and we have total 2, 3, and 4 carbons. So we have to go from here to here. Again, you have to add carbons. So if you have an alkyne, recall from organic 1 that both of these hydrogens, they are acidic. And so the first thing that you would want to do is you would want to treat it with NaNH2, because that's a basic enough compound which is going to take off that acidic alkynic proton. So ethine is going to essentially give you sodium acetylide. Let me draw that. HC, same carbon. It doesn't matter, it's symmetrical, but it's a good idea to use the same carbon so you can follow along the number of carbons, 1 and 2. And of course, since we want to increase the carbon chain, and one of the things we have to add is the cyclohexyl ring, you would want to use that. Typically, if it was a tertiary, you would not get a substitution at all. You would basically get only an elimination. But in this case, you can make it go. So you get your alkyne, and that will then be treated with methyl iodide. So the same kind of chemistry. One more time. And that will give you cyclohexyl ring, carbon, and methyl. When you treat this with mercury acid, so H2SO4, and water, this is going to give you the ketone. And now that ketone can take up that fourth carbon, because you might be wondering, it's a butanol, and right now we had 3 in the chain, so how can you incorporate that? You realize that we had to get a tertiary alcohol at the end, so I had to do a Grignard at some point of time anyways, so I chose to keep that as the last step. And so chain elongation followed by Grignard reaction, and you get your molecule in question. You can carry out the same conversion, this repair, in another manner, and I'm going to discuss that just in a second. Realize that since you can add carbons using a Grignard, if there is some method that you would be able to convert the acetylene into a carbonyl compound. So since it's a 2-carbon alkyne, when you subject that to treatment with mercury H3O plus, and that H3O plus is basically coming from H2SO4 and H2O, that's going to give you an aldehyde because it's a terminal position. So either of the two, those are identical conditions. You could do the same thing with BH3THF, H2O2, and AOH, that reaction condition as well. And now when you treat that with a Grignard reagent and follow it with hydrolysis, this aldehyde is going to give you a secondary alcohol. And of course, that will have to be oxidized first to get the ketone. Now realize we have the 2-hexyl part, so this is my second carbon. I'm supposed to have a 2-butanol, so I'm supposed to convert the C double bond O into the OH, and that would bring 2 of the carbons, and so I only need to bring 2 more carbons. So now if I subject that to treatment with an ethyl-based magnesium bromide and follow that with hydronium ion, I'm going to get the desired molecule in question. All right, let's go forward. Let's think about more prepared problems. Okay, we have to generate trans-2-methyl-2,3-butane-diol from 2-methyl-2-butene. So again, 2-methyl-2-butene would mean this molecule, and trans-2-methyl-2,3-butane-diol means I have one pointing up, the other. So the relative stereochemistry is trans. And so how do we go about that? That's pretty straightforward. You can hopefully envision that trans molecule can be obtained if you have an epoxide. and the epoxide can be generated from a double bond using MCPBA. So really, this is a two-step process. You will treat the alkene with MCPBA and dichloromethane as your solvent, and then you're going to ring open your epoxide with water in presence of an acid, and that will give you your desired molecule. Now, if tomorrow you wanted to change your target to, let's say, you wanted to get a double bond O at one of the locations, realize that a tertiary alcohol is not going to go through an oxidation, so you don't have to protect it or anything, but once that diol is obtained, you can simply carry out an oxidation and convert that secondary alcohol into the corresponding carbonyl. All right, one of the questions that was asked was you have to synthesize this ether from your choice of alcohol or alkyl halide. So basically we are carrying out Williamson ether synthesis. And so the one thing that I said in class was you have to evaluate what's connected to the oxygen. If both of those are primary, you can use whichever alcohol, whichever alkyl halide. However, if one of the sides is secondary, then you want to fixate that particular one as your alcohol. Treat that with the base that will give you the alkoxide, and then that you will treat that with the 2-carbon chain to carry out the substitution reaction and get your product. So pretty straightforward there. Another one, 3-methyl-1-butanol from 2-propanol. Realize that this 2-propanol, this part, with the OH, since you can convert the OH into an alkyl halide and a Grignard reagent, so this has the potential to end up being here. And so if you count the carbons, first off, if you count the carbons, you have 3 carbons here. You have 1, 2, 3, and then 4 and 5. That's how in my head I am seeing that I have added 2 carbons. So if you have added 2 carbons linearly, I said in class that one very good way to go about that would be using an epoxide. And so if this part 4 and 5 is going to come from the epoxide, that would mean that you will need to convert the alcohol into the alkyl halide. So treat it with PBr3, treat that with magnesium ether, dry conditions, 0 degrees Celsius. That gives you your Grignard reagent. And now treat that with the epoxide. Since this is going to be basic in nature, it's going to, in this case, it doesn't matter because both the sides are same. But if there was a choice, it will open in least substituted direction in that epoxide. And upon further hydrolysis, it's going to pick up that proton. So I'm going to say this is 4, this is 5, and we have added the isopropyl group. And you're done. That is it. One thing which several of you just cannot see is that if you have a tertiary alcohol that's getting generated, it can be formed in several ways. Realize you have to add carbons on the carbonyl. So one option would be if you can keep this part intact, and that would mean it's coming from benzophenone. That means what have you added? You have added a 1-carbon chain. And after hydrolysis, you would have the tertiary alcohol in question. Another way to visualize this would be if you keep the phenyl and the methyl and add the phenyl from the Grignard. So now you will be talking about acetophenone, phenyl magnesium bromide, and that after hydrolysis is going to give you your tertiary alcohol. A third method would be if you have an ester, and we've talked about that in good length, that since esters of any kind for that matter, they have the potential to generate generate your molecule, you in this case realize that the methyl is one and the phenyl, there's two of those. So that means I will have to start with CH3, C double bond O. OCH3, you could have ethyl if you want to. That doesn't matter. This part does not matter. So now if you treat that with an excess amount of phenyl magnesium bromide, in the first round, one of the phenols that's going to attack ring is, or the carbonyl is going to get polarized, and when the electrons come back, this whole part is going to go away. So your first product is going to look like pH C double bond OCH3, and then another molecule of the pH MgBr is going to come in, and pretty much the same reaction as you see in orange is going to take place, and you would get your tertiary alcohol. So you can go carry out the reaction with benzophenone, acetophenone, as well as an ester. Now, one thing that you have to keep in mind is that if you're using an ester, then the group that repeats itself, it's important that there should be one group which you should have more than one occurrence of it, and in this case that happens to be the phenyl group. If a choice is that you have, let's say, methyl, and you put in excess of the methyl group again, methyl magnesium bromide, that's not going to cut it. This is not going to give you the desired product. Also, if you were given, let's say, pH CO, and you treat that with excess of methyl magnesium bromide, even that is not going to give you the product, because it's going to bring in two methyl groups at the C double bond O, not two phenyl groups, which is what you have.